Okay, let's move ahead with regard to data processing and management. Previous lectures we were talking about the data structures and how do we store and create these different types of data structures. Then we're going to move ahead now talking about data processing and management, assuming that we already collected and stored the data in a particular structure. This is the table of content of the lecture. I'm going to give you a basic introduction of what our intent is in terms of doing the analysis and data and doing the processing and management of the data, why we need to organize the data into data layers for analysis, and then I'm going to go through some of the common data manipulation analysis capabilities that GIS software has in most of them. Okay, so it's very important that you know beforehand, before you buy or you download some of the free GIS software, some of their functionalities. Now, GIS spatial analysis function distinguishes from other types of information system. Now, in GIS, when you compare GIS with probably a CAD system or probably a business information system, what differentiates GIS from the other types of information system is the ability to show that spatial relationship between features, between data sets, and make decisions such that it integrates the attribute information together with the spatial data and the multiple data sources available, such that better decisions are made. This function utilizes the spatial and non-spatial attributes, so spatial being your maps, non-spatial attribute tables, is like your tables attached or linked to your spatial data, to answer the questions about the real world, a set of questions. Your GIS is going to be a system where you answer one or many questions that the end user would like to answer. Know that GIS models are designed to mimic only selected aspects of reality. You will be required to come up with a conceptual model of what is that phenomena that you are trying to model. What am I going to do in terms of creating a model to be able to address the concerns, or to be able to map the particular phenomena to answer these questions. Now, your model is going to be very selective in terms of the type of the data sets you're going to use and the format, the structure, but also what data set is important for my intended application. Generally, the more factors that a model takes into account, the more complex the application becomes. So the more data you take into consideration, the more complex will be your GIS application. Note well that the more information, the more processing, the more expensive it's going to be for that system in terms of implementing it, in terms of collecting the necessary data and doing the work that's required to provide or develop that application. The more complex model may or may not provide better answers. So you might say, well, let's go ahead and collect all of the possible data sets. Yeah, but the problem with that is that the more time you spend out in the field or collecting data, purchasing data, the more expensive the system comes in, it becomes. And your client is not going to be happy if he has to pay a large bill at the end of your GIS application. So you try to strike a balance as to the best or the minimum amount of data sets to get the best answers. It depends upon the questions to be answered, to be addressed, and the analyzing capabilities of the GIS software being used. So you need to do some work before you actually do the data collection and also the analysis. This is a little diagram of the type of analysis that we might want to do in the future if you're looking at habitat classes, classifying the data in terms of different habitats. Or looking at vegetative growth stages. I want to be able to look at vegetation and identify the different stages in terms of a time period. or ecological land units. I want to be able to identify. You don't go out there in the field to map ecological land units. What you do is you use a number of data sets and processing, GIS processing, to come up with a map that would show me ecological land units. And similarly, vegetation, vegetative growth stages, and habitat classes. Models are used sometimes repeatedly to perform analysis that test alternative scenarios. So my model, let's say for example, I have a simple model and I ran it the first time wrong and the results, it wasn't satisfactory to the client. Then I have to go back and do the cyclic process again of collecting new data or more accurate data and running through different scenarios or alternatives. To develop the best answers from the information available requires a systematic framing of the questions to be addressed. So yes, you're going to have your GIS application answering questions, but you need to know before what these questions are, and these questions will be defined by your clients through your initial meetings with your clients. And then once you know what the questions the clients want answered, then you would go and in your development of your GIS application, you would prepare the criteria, the SQL queries that you would query the database, the spatial and attribute tables. And these queries are linked to the questions that your clients would want to be answered. There's often a storage tendency to begin with the questions to be answered and the data needed. So sometimes some developers will say, well, okay, what are these questions? What are data sets that I have, free data sets, and what are some of the questions I can have answered? Now, please note that your client might not know some or all of the questions that the system can answer. So it is your opportunity to make or sell your applications and its versatility in terms of answering questions that the client may not have asked initially, but would appreciate that additional functionality in the GIS application. The analysis functions available in GIS and the organization of the data influences the usefulness of the end result. Remember, you will be preparing applications not for your personal use, but actually for your clients. So, and your clients work within an organization. So you want to be making sure that all of the people involved in the decision-making process in the organization are on board with your initiative in developing GIS application, such that you are producing results that are going to be beneficial to the organization. It is very important that you organize data for analysis in a specific form in terms of you have a plan before. You have a plan of what sort of data sets is critical for my application. And I always draw reference to what is the intended use of the GIS application result. That will give you an idea of what sort of data you might be requiring in your GIS application. Geographic information are organized within a GIS so as to optimize the convenience and efficiency with which they are used. So if I'm going to use probably an orthophoto, this is a raster structure with some cadastral or parcel information or lots information, zoning maps, tax maps that I would get, land use and any administrative boundaries. All of these should be in the minds of the developer. How am I going to use all of this information that's going to help in answering the multiple questions that my client wants answered? But more importantly, how do I organize these data sets? All right? How do I display it? Do I look at classifying the raster image, or do I look at classifying the vector data? Things like that. The form of organization chosen will be influenced by, for example, number one is the type of data. Is it raster structure? Is it vector structure? It will also be influenced by the type of analysis to be performed. What type of analysis am I looking at? Site suitability analysis? Am I looking at creating buffers? Am I looking at creating 3D models? Another influencing factor that will influence the form of the, in terms of the how the data is organized, is the method used to encode the data. What sort of methods used to capture the data? Is it remote sensing, satellite imagery? Is it photogrammetry? Is it land surveying techniques? Things like that. It's very important. Geographic information is usually organized as a set of feature classes. Example, I'm going to have one data layer, which is in GIS terminology. We're going to have store all of the roads in one layer. We're going to store all the streams on one layer, or the land use in another layer. And in other GIS software, it's referred to as some sort of a generic data layer name. Here's an example of a land suitability study where they did some spatial overlay analysis. They have a number of data sets of the same study area, one being vegetation, the other being floodplains, and the third is soil type. Overlaid all three of them, and they come up with a final map where they come up with land suitability map and a different classification of it. Very useful map. It conveys to the end user information that they didn't have before. So the area in yellow would indicate the areas that are land suitable for a particular intended use. Data layers. I'm using data layers here, as I said, as a generic term. A data layer consists of a set of logically related geographic features and their attributes. So a data layer in any GIS software refers to that single data set that is going to be storing either point, line, or polygons of a particular phenomena that will be overlaid onto other data layers. The features to be grouped in a single data layer are chosen for convenience of the users, and is also chosen based upon the conceptual model of the particular phenomena that you are going to model. Organization principle may be to group similar feature types. If I have a particular feature class or data layer, and I want to be able to group, let's say I have road network, I want to be able to group the first class roads as 1, second class roads as 2, and third class roads as 3. That's what it's saying here. For example, roads and railroads may be combined as a single transportation data layer, and I can separate that out once it's defined in my attribute table which line features are my roads and which line features are my railways. There are two slides. Let's look at these two slides in terms of the data layers. We have here layer A, layer B. Layer A is a set of polygons, layer B is a set of lines. We take one and overlay with the other, A overlaid with B. Remember, when we do the overlaying of different layers, the attribute is also combined. So the final result we're going to have here is the overlay layer together with the attributes from layers A and B. Layers A and layers B. Simple concept, but applicable to all GIS analysis. This is another example here where we overlay roads. We have a roads data set overlaying counties. When we overlay roads with counties, we get a final map where each part or segment of the road would have or get the information of where it falls in the various counties. So my roads have a specific attribute table, and my counties have a specific attribute table. When I take the roads overlay with counties, I would have a roads map, but the roads map is going to have where each segment of the road fall within the county. So here we have Highway 22. It fell in county name is Black. So this is merged with that. And the final result is a roads layer. Now, let's talk about some of the generic data manipulation analysis tools that most GIS software has to offer. I have listed about 10 of them, and we're going to discuss each one of them generally in the following slides of their capabilities. Now, know that GIS software provides a set of tools, and it's a tools where it is a set of tools that you would use to build your application together with the data that you would have collected. Okay, so these are some of the tools, and this is the 10 generic type tools. In the commercial software, there are hundreds of tools available. Alright, so very, very extensive. Your GIS analysis capability, one of the common tools that's shared across the different GIS software is that the ability to do some coordinate transformation. They would have programmed into their software the general mathematical expression in order to convert from, let's say, one coordinate system to another coordinate system. Okay, so if this is the original coordinate system here, I want to take this and transform it to a new coordinate system. And it requires some rotation matrices and some translation, and there will be some different types of parameters included in the formula. But this is the general matrix representation of how the transformation is done. It is used to convert coordinate data within one frame of reference to a coordinate data in another frame of reference. So it might be that when you convert from one frame of reference or one coordinate system, you might have to do some scaling of the original data, or it might be a bit skewed, or translation, or might have to rotate it. So all of this is programmable using mathematics. It's programmed in mathematics using the programming language. All right, so your GIS software should be able to do some coordinate transformation. It's used for a variety of applications, changing one map projection to another map projection. Note here that in order to convert from one to the other, the original, all the data sets must have a specific, must have a map projection defined. Otherwise, you can't convert from undefined to a defined. We can also use it to change from digitizer coordinate from a digitizing table to probably UTM coordinate system. Also use the removal of distortion in your documents. Very used for a variety of applications. Changing the scale, rotation, and the shift, if I want to do all that. Transformations, there are different types of transformation in GIS. If I want to maintain the scale, rotation, and shift, then I'll do a conformal transformation. Common term being used in GIS. If I want to maintain the scale, rotation, shift with a stretch maintain, then I'll do an affine transformation. Or if I want to do a higher order transformation using polynomials, I'll choose that transformation. All three of these are already programmed in the standard GIS software. This little graphic here shows the difference in terms of the conformal, affine, and polynomial. You have actually between the affine and polynomial. If my original data is as shown there, I want to transform it to a affine projection. You can see the data actually a bit skewed based upon its original. If I want to do a polynomial, second order or third order, you can see the variations being shown up here. Your GIS software should be able to do map join or edge matching. This is the process of removing inconsistencies at the edge of maps from compiled data, map data. For example, if I have digitized, let's say 100 maps, I want to be able to merge these maps into one seamless map. Then I'm talking about doing a map join or edge matching. Edge matching all constitute to one function. Edge match can be considered as a tie. Map join is putting them together and merging them into one seamless map. This is an example of what edge matching entails. Here we have two maps, sheet A, map sheet B, both digitized separately. Well, in order to merge them together, they did what this GIS software did was to take the two of them and actually match the edges of where that pond area is located, and match it so that it closes the entire polygon. Very useful tool in combining multiple maps. Now, note that if you're doing edge matching, if you were to do that manually, merge one to the other, there's a likelihood that what would have happened when one map, let's say in this map here, map A, it was digitized, and then map B, it was digitized. This common boundary is very unlikely that the operator that was doing the digitizing would have followed exactly where those lines are. If we were to zoom in into those areas, there would be multiple polygons. Those polygons are what we refer to as slivers. Okay, what it should have done is that when the matching, when you merge these two polygons, it should have been a common boundary. But because it was digitized twice, you have these polygons when you zoom in. Those are errors. Now, when you do a map merge and edge matching, it would have removed these slivers, and we call these little polygons slivers. Note the terminology. Your GIS software should be able to do some windowing. It's a function allowing the user to define a specific geographic area which is to be used to delimit a piece of map area. Windowing can be looked upon as if I define a window to zoom into. I'm interested in my study area, I'll zoom in, I'll define a window to zoom in. Or if I want, windowing could also be referred to as select for me all of the features that fall within that window I would define using my mouse. So I'll have a window, I want to select all of those features that fall within that window. Map features and associated attributes can be retrieved using windows for display analysis and manipulation. I have an example of what windowing looks like. Here you have an image. It's an interactive map, this image I got online of tax office, and what they have here is actually a magnifying glass. Is a common I can use in most of the graphic packages, GIS being one of them, of course. I can zoom in or zoom out and define my window. So if this is my study area, I can use click on that particular tool and define the window. Usually select one corner of that window and drag the mouse across and you get the other corner. Or if I want to select cells or maps that fall within a particular window, so I would define my window, one corner here and the other corner, and then the system will select for me all those are in yellow. The system report back the areas shown up in yellow are the areas that were selected. So it's another way of using windows. This here I try to give you a graphic in terms of how do we define windows, what is involved in defining windows when we're selecting features. I have a map, a soil map. I want to select polygons 3 and 4. So I define a window starting from this location or any location and make sure that my polygons, all that I'm interested in, fall within that window. And when we do that, is that the final map, the selected two polygons, 3 and 4, is selected and also together with its attribute information. Very useful in different scenarios. The GIS software should be able to do coordinate filtering. It's a process of weeding out superfluous coordinates. And it is the process by which we will remove repetitive or coordinates where the coordinates are too close to each other. Why? Because remember, in a vector structure, the coordinates are stored, so I don't want to have unnecessary coordinates. It's used to generalize maps and reduce requirement for computer storage. Other terms used in terms of coordinate filtering, line thinning is another term, data compression is another term being used. And coordinate filtering, there are a number of criteria. It can be based upon a certain distance interval, where the system will say, well, wherever, if in the database, every 10 meters, I would store a point. All right. If I have any coordinates that are less than 10 meters, then I'll remove them out. Or based upon a time interval, or angles, or thresholds, second difference gradient, things like that. So it's very flexible in terms of doing some coordinate filtering, minimizing or compressing in particular your vector data. This is an example of your line thinning. So what you would have done was digitize this point here, this point. What the system did was actually, when you do a line thinning, it will smooth off these lines and make it a bit more realistic rather than these jagged edges that you will have captured. And sometimes it might be that you zoom in too much and you actually overshoot certain areas. So the line that's shown up in red is a smooth out line after line thinning. Okay? And this is the same thing using a different interpolation. Thiessen polygon is another tool available in most GIS software. It's the creation of polygons or areas around randomly spaced point locations. So if I have some sample points of, let's say, soil types. So I went out in the field and captured and did some soil tests, different location. I want to extend those soil tests to on a map where it's referring to a polygon area. So move from point data to polygon data. We do that using what we call Thiessen polygon. It is carried out by dividing equally the distance between paired points, then generating perpendicular bisectors, or midpoint. That's what I'm saying, bisectors, which are then extended to intersect and form the areas. The process is used for creating polygons, mapping and analyzing qualitative data where continuous coverage is desired. So Thiessen polygons, know that it's one way of using your original point location of whatever phenomena you went out there to capture, and using that to create polygons. This is an example. A point data set was used, and using the Thiessen polygon tool, the final map. So this is the original point data, and I have here a Thiessen polygon map where each one of those observed points will be at a specific location, will remain at some location, but a boundary is defined, which is a Thiessen polygon boundary. So we move from point level information to polygon level. The attributes associated with this observed point will be for reference the entire polygon. Very useful tool. This is another example of points from which Thiessen polygons are generated. The closer the points are, the more dense or the more detailed will be your Thiessen polygons. Alright, so you have a lot of smaller Thiessen polygons here, more Thiessen polygons, etc. And in areas where it's more dispersed, the Thiessen polygons are larger. Alright, this concludes our discussion about data processing. As I said in previous lectures, download the notes PowerPoint presentation, go over the material, make sure you understand it, and we will continue with the next class